Gérard, tu m'entends?
Le Nobel Trio est le résultat de la rencontre entre plusieurs inspirations. La mission de TEDxSaclay inspirée pour agir, l'équipe talentueuse et pleine de vie de TEDxSaclay, et des hommes et des femmes formidables, 3 prix Nobel de physique qui ont accepté de nous parler d'eux, de leurs histoires de physique et des liens entre la physique et Terre notre vaisseau, le thème 2021 de TEDxSaclay. C'est avec un immense plaisir que je vous présente le Nobel Trio, enregistré lors de la 6e édition du TEDxSaclay pendant la pandémie de Covid-19 le 24 juin 2021.
Hello everyone and welcome. Sorry for the delay. We are very happy to be with you today for this discussion with our 3 Nobel Prize winners. My name is Mélodie. I am a volunteer with TEDxSaclay and I'm very happy to be the master of ceremony today. We just had a few technical issues. If you have technical issues, please comment in the feed on the right of your screen and our technical team will be in touch. I know the session today is international. We have people connecting from all around the world or at least 2 different countries. So please comment in the feed, tell us where you're connecting from. So it will make us happy to know where you're from. We are really thrilled to host this discussion today with our TEDx speaker, Gérard Mourou, and his 2 fellow Nobel Prize winners, Donna Strickland and Art McDonald. The humans behind the Nobel laureates are really inspiring and fascinating, as we have discovered, and as much as their physics, actually. So we hope you all will enjoy getting to know them. We are ready to begin, so I will invite on stage the president of the University of Paris-Saclay, located 20 kilometers south of Paris, and the principal of Queen's University in South Ontario in Canada. Mrs. Retailleau, I will let you first introduce the University of Paris-Saclay and tell a few words about Gérard Mourou, and then we will have Patrick Deane introduce the University of Queen's and our 2 other laureates, Donna Strickland and Art McDonald. Sylvie Retailleau, the floor is yours.
Thank you very much. So for the presentation of Paris-Saclay University, first to say that Paris-Saclay University was established in January 2020, and we cover 13% of all French research, and we're ranked 14th overall, first in mathematics, in our first appearance in the global academic ranking of world universities. Another particular characteristic of our university is the strong ties between education, research, industry, business and innovation in an outstanding ecosystem in the South Paris area. The first of our university laboratories was the Institute of Nuclear Physics of Orsay, set up by Frédéric and Irène Joliot-Curie in 1956. And Irène Joliot-Curie, who was awarded the Nobel Prize in 1935 with her husband, Frédéric, for the discovery of artificial radioactivity, was actually the daughter of Pierre and Marie Curie. Added to this, Pierre-Gilles de Gennes and Albert Fert, 2 Nobel Prize winners of physics, are also affiliated with University Paris-Saclay. And we have likewise many ties with Gérard Mourou, Nobel Prize winner from the Institut Polytechnique de Paris, which is also on the Plateau de Saclay. So I am really delighted to introduce Professor Gérard Mourou, co-recipient with Professor Donna Strickland of the 2018 Nobel Prize in Physics for their method of generating high-intensity ultra-short optical pulses. Their method of stretching, amplifying, and then compressing laser light is able to deliver a power equivalent to 100 times the world's electricity grid over the extraordinarily short duration of 1 femtosecond or 1 millionth of billionths of a second. Originally from Albertville in the French Alpes, Gérard Mourou studied at the University of Grenoble and also Université de Laval in Quebec before obtaining his doctorate at the University of Paris. He crisscrossed the Atlantic many times after that and working at the University of California in San Diego, at the Laboratory of Applied Optics in France, before moving to the University of Rochester in New York, where he and his doctoral student Donna Strickland developed shaped pulse amplification. After a stint in Michigan, Professor Mourou returned to France as the director of the Laboratory of Applied Optics. Since its discovery in 1985, shaped pulse amplification has seen a multitude of applications. The technology is used in laser eye surgery to produce perfect cuts that do not damage surrounding tissue. Other applications that Gérard is going to tell us about include particle acceleration for the use in high-energy colliders, zapping space debris in orbit around our planet, the transmutation of dangerous radioactive waste generated by nuclear reactors into more benign isotopes, and perhaps nuclear fusion of light elements, an efficient, clean type of nuclear energy also. Thank you very much.
Queen's University is 180 years old this year, which makes it older than the nation of Canada itself. And over that time, it has had an important role to play in shaping our country, particularly in policy and government. So the growth of the university has in some senses gone in parallel with the growth of the country. Queen's is now a research-intensive university and a member of the U15 group of Canadian research-intensive universities, a medical doctoral university with great strength in a number of areas, of which particle astrophysics is one. We're now very much focused on maximizing our impact, and most recently in the Times Higher Education Impact Rankings, ranked 5th in the world. I'm very pleased to join President Retailleau today to introduce our 3 Nobel laureates, particularly because of the developing partnership between Queen's University and Université Paris-Saclay. These kinds of collaborations are critical for the advancement of science, of physics in particular, both in the research enterprise and in communicating the results of that work to the broader public. We are very excited about growing that partnership with Paris-Saclay and the opportunity to work together to advance scientific understanding and to maximize the impact of our research for the benefit of society. So as the Canadian representative here, it's my great pleasure to introduce 2 amazing Nobel laureates in physics. Dr. Donna Strickland is the 3rd woman to be awarded the Nobel Prize in Physics and the 5th of 6 Canadians. The award, which she shared with Gérard Mourou, was based on her very first article published as a PhD student at the University of Rochester in 1985. Originally from Guelph in southwest Ontario, Canada, Donna studied engineering physics at McMaster University before heading to Rochester. She worked at Lawrence Livermore National Laboratory in California and Princeton University before returning to Canada as a professor of physics at the University of Waterloo. Donna Strickland's doctoral project was to develop a method of producing ultra-fast, ultra-powerful laser pulses in a bid to understand multi-photon optics. By coincidence, a field pioneered by the second woman to receive a physics Nobel, Maria Goeppert-Mayer. The difficulty in this was that the high-intensity beams would destroy the amplification device before reaching the desired power. The solution that Gérard thought up and Donna implemented in the laboratory was to first stretch the laser pulses by exploiting their chirped multi-wavelength nature before amplifying them and recompressing them. As mentioned by my colleague Dr. Retailleau, this allows for an astounding amount of energy to be delivered in the period of a femtosecond, and thus the exploration of fundamental physics in the high-intensity regime. Professor Strickland now leads the ultrafast laser group at the University of Waterloo, which actively works on intense laser matter interactions, nonlinear optics, and short pulse intense laser systems, including an intriguing technique called Coulomb explosion spectroscopy. And last, but certainly not least, from my own institution of Queen's University, Arthur B. McDonald is the recipient of the 2015 Nobel Prize in Physics shared with Takaaki Kajita for the discovery of neutrino oscillations, which shows that neutrinos have mass. Originally from Cape Breton Island in Nova Scotia on the east coast of Canada, Art McDonald studied at Dalhousie University before obtaining his PhD at Caltech in 1969. He worked at the Chalk River Nuclear Laboratories and was a professor at Princeton before joining Queen's in 1989, where he is the Gordon and Patricia Gray Chair in Particle Astrophysics Emeritus in the Department of Physics, Engineering Physics, and Astronomy. Professor McDonald is a particle astrophysicist. He was the director of the Sudbury Neutrino Observatory SNO experiment, which is located more than 2 kilometers underground in an active nickel mine in Ontario and is the size of a 10-story building. SNO detects neutrinos from nuclear fusion in the sun, which are so weakly interacting that they travel through the Earth unimpeded. Unlike previous observatories, SNO was able to measure all 3 varieties, whimsically called flavors, of neutrinos. From its inception in 1989 to final results in 2001, Art and his 200-member team were able to show that the neutrinos produced in the sun change from one flavor to another as they travel to Earth. Neutrinos, which had previously been reported missing, were simply disguising themselves in a different flavor, definitively proving that they should have a non-zero mass. Since the SNO experiment, Professor McDonald has pivoted to the search for dark matter with large-scale liquid argon experiments. However, his most recent claim to fame is of a different variety. Together with members of the global Archon Dark Matter collaboration, he co-led the development of the mechanical ventilator Milano, a low-cost, safe, and reliable ventilator for COVID-19 patients that is easy to replicate and operate. Approved in the US and Canada, 7,300 units have already been produced and delivered to the Canadian government for the Canadian stockpile. They are also being considered for donation to other countries in need for the fight against COVID-19.
So I suggest now that I introduce to you our 2 hosts for today. We have Aaron Vincent in Canada and Fabrice Nicot in France. Aaron, you are an assistant professor at the University of Queen. And Fabrice, you are a French journalist at a monthly scientific review called Science and Avenir. Aaron and Fabrice will lead the interview in 2 phases today. We'll have a first phase relating to the experience and the stories as scientists of our laureates. And then we will have the relationship between physics and the theme of our conference today, Terre, notre vaisseau, or Spaceship Earth. So enjoy, and I'll leave the stage to Aaron, Fabrice, and our guests.
Thank you. Thank you, Mélodie. my microphone is on. No, it's better. Dear all, during the preparation for this interview with Donna, Art, and Gérard, I discovered that there is a common link between Brian May from the rock band Queen, the Toronto Maple Leafs hockey team captains, and the Pope. These are all people that you have met thanks to the Nobel Prize. I think it's a good illustration of how this prize can change lives. But let's start with how you got there. Donna, Art, Gérard, how did it start? By a particular aptitude, a great teacher, a desire to succeed, your parents, perhaps first. So, Donna, for example.
Oh, I get to start. Thank you. Thank you very much, Fabrice. I've said this many times. I think it was just a natural path for me to take. Both of my parents were educated, and it was rare for them. My mother was from a small farming village, so not very many girls went off to university, but she was one of the few. My dad came from a fishing village in Nova Scotia, where they didn't even have the final grade of high school. So the fact that they both went off to university was talked about a lot. So it was very clear that we were expected to go to university. And I just found math and physics fun. So I didn't have too far to sway. I knew I was going to do math and physics. And when I just first heard about lasers, to me, they just sounded so cool. I just thought I have to do that. So off I went. And I asked a grad student at McMaster where to go. And one of the places they suggested was Rochester. So, and it was a fellow Canadian, I will say, that met me my very first week in Rochester. And when he asked me what I wanted to do, I said, oh, I want to do lasers. He goes, I know the guy you should meet. And off he goes. So this is Bezos, of course, Gérard. And he took me that very first week in Rochester to meet Gérard and see his beautiful lasers. So that's the beginning for me.
Thank you, Donna. And Art, you talk about, I remember, great mentors.
Indeed. So neither of my parents had the opportunity to go to university. My father actually, for the first 3 years of my life, was with the Canadian forces in fighting in Europe. And my mother certainly had the capabilities, but never the opportunity. But I come from Cape Breton, and it's a part of Nova Scotia also, where Donna's father was from. And there's a great emphasis on education there. I had a very good mathematics teacher in high school. And so I actually, we had in my class in high school, maybe one fifth of the class overall size, we had, out of about 30 people, we had 2 PhDs in mathematics and 1 PhD in physics, to show you the influence of Bob Tate, my teacher. So I went to university knowing that I liked math and that I wanted to apply it somewhere. And in my case, I started with first year physics, and I could really do it. I just was very good at it. And so kids ask me these days, how do you choose a career? And what I say to them is, well, look for something that would be fun every day when you get up in the morning, which I can now say about 60 years later is still true. And see if you're any good at it. Try a few things like that and see which ones you're good at, and then pick from them in terms of a career. And so I just followed my nose, and mentors were very important to me.
And still fun after all these years. Fantastic.
So Gérard, was it a similar story for you?
Oh yeah, I mean, for me it was, my dad was an engineer in an electric company known as EDF. It's very power company, and it was a beginning at that time. We were in Savoy, and he was at the time where, hydro was very, very big in Savoy because you have a lot of white water and so on. And so my dad was really an engineer, and he was in charge of very large sections of Savoy, where basically, you can also ski, and you have all the best ski resorts, in France. So ski has always been also be important to me. And I remember very, very vividly, one morning, we had breakfast together, and he said, I was maybe 5 or 6, and he said, gee, I had a coffee yesterday with Madame Curie. And so I say, well, big deal. What is she? What is he? Is she? And he said, she's a Nobel Prize winner and so on. I said, wow, Nobel Prize winner, what's that? And of course, he went along, to tell me about it. But what was really important with my dad, it was because, since I was little, I heard about, ampere and volt and watts and so on, and because he was in charge of the electric grid in Savoy, so and all the dams and so on. So I had a really very early peak at the electromagnetism, that. Plus, he was, of course, very excited about astronomy. And I remember when he told me once, that light was going at 300,000 kilometers a second. Wow, that I was struck, And
again, very strong mentor.
Yeah. And then for me, trying to go not as faster than light, but at least trying to dominate lights like we do, with ultra short pulses. With ultra short pulses, we can freeze light in fly. This kind of thing has always been important, and also because I remember my dad talking about power of dams at that time. It was really megawatts, something like this. And so when the first time we had megawatts, with the pulses of 1 joule in a microsecond or so, something like this, you had megawatt, and we could really be more powerful than laser and dam. So that was the context, of and so I was a little bit maybe fortunate.
So just to move to
such a dad.
Thank you. Just to move to the next question. So a lot of people have an idea of science that I think comes from school, right? That you could describe it as learning facts about nature. But that's not really what science is. And I think the three of you, so Art, you work on neutrinos, and Gérard and Donna, you work on lasers. You've described science as being about having fun. So could you describe very, very briefly what science actually is and what makes it fun? So maybe we'll start with Donna again.
Okay. Well, there's different reasons why science is fun. And I think for those of us who get to work in optics, I say, we're the ones who actually get to see our experiments. We actually put infrared light into something simple like water, and out comes every color of the rainbow. And when this first happened back in the 80s, scientists didn't know why. It just happened. And some scientists went ahead and used that. But science is really about asking, why does this work? And as you're saying, in school, we spend so much time trying to teach the science other people have learned. And so it's about learning these facts. And you need that in order to understand. But doing science is really asking the question, why? And trying to figure out why it is the world works the way it does. And so it took a lot of years, but we now do know why all those colors come out. It's still fun to see. It's just like a magic thing. But it's wondering why.
Would you agree with that, Art?
So yes, absolutely. And once again, it's a question of when you wake up in the morning and say, okay, what I'm going to do today, and you go into the laboratory, I'm speaking as an physicist, and you try something, and you either find that the outcome of the experiment is something that you expected, or it's something that you didn't expect. But it's always exciting. And if you expected it, then you move to the next step. If you didn't expect it, then you have to figure out why. And so it's like a big game with nature that you're doing every day. In the case of the experiment I was involved in, I was working with more than 100 other people at any given time in the course of an experiment, which took us 15 years to get to the point where we had built this enormous detector and get the results. But when we got the results, which in fact were one of two possibilities and had a significant impact, everybody on that team, which I was fortunate enough to lead, were very excited. It was a eureka moment among all of us. And that's fun as well when you work collaboratively with other people, which scientists do in a very broad way.
Did you expect the result that you get? Was it a surprise?
Well, in our case, we had a question of experience from a previous experiment where there were too few of one of the three types of neutrinos coming from the sun as measured, an experiment that could only measure that type of neutrinos. The question was, is the problem the experiment, or is the problem the calculations of how many neutrinos are produced in the nuclear reactions that power the sun, or are there new properties of neutrinos such that they turn into one of the other three types, which is what we found to be the case. And that's the first experience with something that goes beyond what had come to be known as the standard model of particle physics. And so it was going to teach us something new. So we had either the possibility that we would learn something about the sun or learn something about neutrinos. But first we had to do the experiment, which was not simple in itself.
And the answer is not in the back of the book.
No, the answer turned out to be fairly revolutionary in terms of understanding the physics of neutrinos. But there's a lot more to learn.
Mm-hmm. State of the art of science requires time, money, find the right people at the right place. What is the most challenging aspect of your job as a researcher outside the science itself? Perhaps Gérard.
I'm sorry, I missed your question again. I cannot hear very well here.
Okay. What is the most challenging aspect of your job as a researcher outside the science itself?
Oh, there's so many things. I like music. I like sports. I like these kind of things. So you want to?
I thought about the find the money, find good people for your research. This kind of things.
Yeah. Of course, because you never have. You need three things, right, to do some important work. You need, of course, the idea to start, and then you need the people, and you need the money. Okay, you need the three together, but you never had that, especially at the beginning. So you start little by little, okay, and to build your people around your idea, and a lot of times you have you have, of course, I was very lucky to have very good students like Donna and so on, which goes, of course, when you have a good idea, you find good students relatively easy. And there is one thing which is very important in science, which makes it fun, I think, is serendipity. Serendipity, something that you were not planning, and you find it. And that is is also a big part of that.
Thank you. And Art.
So yeah, Art, you've led a very different experiment. So this is a 200-person scale experiment. Is one particular aspect more challenging than the others in terms of finding people, finding funding, finding interest?
It really is a combination, and you start. Gérard really covered it. You start with a good idea. If you have a good idea, you can often attract very good people, which I was very fortunate to have the opportunity to do. And then the combination of the two is what leads to the funding. Although in our case, because we were asking for a scale which was greater than $50 million in Canada to do this experiment, it was of that significance if we could be successful. But nevertheless, convincing funding agencies, and we basically had to convince a number of different funding sources to come together. That took about 5 years from the original formation of the collaboration to the point where we got some money to, we got all the money we needed to do the project. And so there's a certain amount of politics, a certain amount of diplomacy. Certainly when you're dealing with 200 people in science, you have to apply a lot of diplomacy in making sure that you develop a consensus on any given major topic. And if you do, then the people can get behind that consensus and apply their skills in a very good way. So those are the sorts of challenges that you run into.
So it's important for science to be an inclusive endeavor on sort of all axes: gender, ethnicity, sexual orientation. And so Donna, I'm sure you're tired of getting questions like this. So I'm going to actually ask the men. So why is this important for you when you do science, and then sort of how did you address it? How did you see it in building your research teams?
Well, I think we have to refer to Donna. I think she has the experience in this topic and may want to speak first. Be happy to answer, but let's ask Donna first.
I have to say, I think they asked you first because I said I didn't want to answer this question.
All right, never mind. I will say the approach we took in our project, as I said, had any time more than 100 people, was to simply look for the best people. And as it turns out, a very large fraction of those people were women. We were less successful in terms of diversity, in terms of race, and to a large degree, I don't know about sexual orientation, as it turns out, because we started back in the 1980s with our experiment. These days, I think we have diversity within the projects I'm involved in, and we go out of our way to make it such that it's a level playing field for everyone. And in some instances where we see lack of diversity, we're attempting to emphasize that. But in physics, just talking about gender imbalance to begin with, it's poor in the physics, in physics in general, particularly at the faculty level, for example. And I'm very pleased to say that of the roughly 200 students and postdocs that got their degrees or postdoc experience on the Sudbury Neutrino Observatory project, we did a survey 10 years later. And there were about 25% of them had university positions, and about 35% of the people with university positions were female. And so that, I think, is an example of how we tried very hard to simply attract the best capable people, and that was a reasonable fraction of women in that sample.
So I think Gérard and Donna, I've heard you both say that physics should be for everyone, right?
Oh, certainly. Certainly, yeah.
Okay, thank you everyone for this first sequence. I hope you audience enjoyed getting to know our Nobel laureates. And I don't know if you noticed, but I think they're humans, just like you and me. However, though, their science is a lot better than mine, that's for sure. So now I suggest to get on the second theme and see how is the relationship between physics and spaceship Earth. So Aaron and Fabrice, the floor is yours again to talk about this space.
Okay, thank you. Yeah, so Art, as was actually not mentioned in your introduction, but would have been, so you co-led the development, in addition to your work on neutrinos and your current work on dark matter, you co-led the development of the mechanical ventilator Milano, which is this ventilator for use for COVID patients that you developed with an Italian team in a few months, actually, last year. So can you tell us a bit about that? Why were physicists the right team, and how is this a model for, how do you see this as a model for international collaboration when it comes to tackling larger challenges?
Okay, we'll start with this, but I seem to be getting most of the questions. Let's make sure we distribute it to the others as well as we go forward. And I'll try not to take too much time. The experiment that I'm working on, again, with a large international team, led, in fact, by Cristiano Galbiati from Princeton and GSSI in Italy, is looking for dark matter particles underground with a large container of liquid argon, where we look for very faint bursts of light produced by these dark matter particles that penetrate through the rock to the underground location and produce these bursts of light. And we've been able to push the sensitivity slowly from 3 tons at Snow Lab, 50 tons at Gran Sasso Laboratory in Italy, and eventually we hope 400 tons at Snow Lab in Canada. This technology for handling gas, particularly for extracting it from underground so that we get low radioactivity gas, is a technology where our experience was recognized by Christian as being applicable for the production of a ventilator that at the beginning of the project, when he was locked down in Milan in March 2020, clearly was of great need. And so what we found was wonderful in the sense that the scientists who had the same consternation about the situation of this pandemic, but were now offered an opportunity to use the skills they already had to do something concrete and help with the pandemic. They came together. We had a design working on the bench in a week. And of course, we had to go well beyond that. It took 6 months or so to get full approval in Canada in particular. That's where we ended up building them. And we had a contract from the federal government in Canada to build 7,000 of these ventilators that are cheaper, simpler to build, and those are in the stockpile in Canada, and discussions are underway to donate them to other countries in need. And the other element of what we did in terms of international cooperation was to immediately publish our ideas and to come up with a final publication of the final product, open source. So we were not looking for patent rights or anything like that. It can be picked up anywhere in the world and manufactured cheaply and simply. So that's the story of a group of scientists and engineers, which included people from national labs in Canada, who were inspired by the pandemic to work together and do something of value.
Thank you, Art. Donna, you're involved in organizing something called photonics for the environment. Could you tell us a bit about this, and how has the Nobel Prize helped?
Yes, thank you. This is work I started sort of an outcropping from being president of the Optical Society. And it's sort of a public policy, just to sort of get out there and say that optics is important in so many ways. And with the signing of the Paris Accord back in 2015, we thought, okay, this is what governments need to hear, that optics people, just as Art said, you're working on something, but it can be used for something totally different. And we decided that we would start and explain how photonics can be used to measure. And that the point is we need to bring scientists who are working on environmental measurements for a host of different environmental experiments, and people that develop sensors. They don't have to be optical sensors, but optics is out there in a big way. And just try to bring them together. And so we've started this global environmental measurement and monitoring, and we're just trying to get governments on board. I'm certainly trying to get the Canadian government to try to start institutes, networks, whatever, to bring people out of their silos and put them together, because it's going to take a tremendous number of measurements in order to have a really great climate model, climate adaptation. We need to have all of this working together. And so that's one of the things that I am lending my Nobel voice to, because it is easier to get government people to listen to you when you have a Nobel Prize.
And this is not something you were thinking about when developing chirp pulse amplification in the lab in 1985?
Not at all, no.
So, Gérard, I think you just delivered a talk talking about climate change and nuclear energy and sort of scientific solutions to these big challenges. Can you tell us a little bit about your thoughts there?
Well, yeah, and this is, also part of this, you say that this Earth vessel, right? So yeah, I mean, I'm seeing these Earth vessels, moving for 4.5 billion years, and now we may be 200 or 300 years before the end of our trip. And so what we did is we called, you call Houston, and Houston calls back and say, yes, we have solutions to your problems. And the problems I found was maybe needs nuclear energy, and we would like to use nuclear energy, and maybe we may have some safe solution to use nuclear energy by using extreme light. The type of light we have developed with Donna, very, very short bursts and very, very high intensity, so we can really accelerate particles very cheaply and, very easy, very cheaply, small system and so on. And also you can use the phenomenal pressure that you can get from this ultra high intensity pulse, this what the ponderomotive pressures, really to do something like to fuse light elements, like fusion energy is doing, like ITER and so on. So these are the kind of things that you could do with ultra short pulses that we were not thinking, of course, before we did chirp pulse amplifications. It's just an outbreak of these activities, yeah.
So you see these scientific developments as being the solutions to the big climate crises that we're facing?
Well, I mean, I want to be humble, of course, we know that there's a lot of good people working and there is a lot of solution out there, but this certainly is one good solution that we should explore, because right now we don't have the choice. We have, yes, it's good to go to Mars, but before we go to Mars, maybe we should really worry about the planets and devote all our efforts trying to make sure that we don't have we end up the trip, safely, not safely. In the world.
So Art, you have a background in nuclear physics. Do you agree that
nuclear energy is promising?
I
agree substantially. I think that both fission and fusion power are things that really should be considered very substantially in the situation we find ourselves in with respect to the way to avoid the carbon pollution that is affecting our planet so substantially. And in fact, I really feel that fusion power, which is what Gérard was referring to most specifically in terms of potential use of lasers, is something that I feel really should have been and should be more substantially pursued in terms of a potential solution that is longer term with substantial resources available to fuel the power and with a system that has a great capability. So I'm very much in favor of everything that Gérard said in terms of the use of these technologies.
Thank you. So just to end our session before we get to audience questions, so you could translate, I think I told my parents and about the theme of this conference, Terre notre vaisseau, they immediately translated as Spaceship Earth, which turns out to have a nice definition. So it's a worldview that encourages everyone on Earth to act as a harmonious crew towards the greater good. So before we get to the last questions, I guess, Donna, I'll let you have the last word. So what's your perspective on this, both as a scientist and as a crew member of this spaceship?
That's right. I think somehow I'm disheartened in that the world seems to be dividing into two factions rather than us all working together. And I think it is a time for scientists to come together to talk about science and the importance of science. And I think science literacy is one of the things that we're going to have to do better as scientists in order for everybody to understand things like the vaccine did not just appear this year. It took a lot of years of understanding all the different aspects of it. And I think that as a global scientist, and I think this is one of the things that Nobel Prize winners do have to spend some of their time doing, is speaking to the public about its importance. I think, unfortunately, most of the time, the people that tune in to hear us already believe that message, and I haven't figured out how to get to everybody else. But science will play an important role in trying to keep Earth safe from humans, and we have to work together at that.
So may I say, my hope is that the way in which the world has been working together to try to solve our pandemic difficulty that we all find ourselves in will stimulate a greater trust in the ability of the world applying science to try to solve problems that affect everyone. And I'm hoping it'll carry into a public awareness of the way in which cooperation can be successful in dealing with that other threat that we have substantially for our society right now. I think the public is mostly going to accept things based on their experience, and if their experience in dealing with the pandemic through science is positive, perhaps the trust in the ability of science to contribute to our life here on Earth will be extended. And I hope it also extends to governments in terms of the power of international cooperation.
So we have a question from the audience. C'est bon? Okay. So what was the best and the worst things about getting the Nobel Prize?
I'll start. No one else is starting. I think the best part really is it just opens so many doors. It's just incredible. And it was mentioned at the beginning, people that you get to meet, places you get to go, conversations you get to have that you wouldn't normally be welcome into the conversation. The worst, I think, though, for me is maybe too much of a spotlight. And I know myself that I can say completely silly things that maybe could be upsetting to people. And so I've been having to really worry about when I'm speaking, am I saying something that I shouldn't be saying? And I find the spotlight sometimes too much.
Thank you. Art?
Well, I think, as Donna said, it provides opportunities to contribute in ways that you otherwise were not able to contribute before. For example, I was invited to be on a panel to review the overall support for science through the agencies in Canada, which was a very positive experience and which I think has had an impact in terms of such things. What I found was somewhat similar to Donna in that suddenly you are tremendously in demand. I mean, I was probably traveling at least 50% of the time pre-pandemic. In fact, from that perspective, having to stay home was actually a relief in my life. After 5 years of well, more than 50% of my time on the road. That was fascinating. I learned a lot in the process, but it does get tiring after a while. And this year has given me an opportunity to get back into research, albeit remotely, in a more substantial way. So it's a different life. You really have to be careful, as Donna said, as to what you say. There was another Nobel Prize winner shortly after I got the prize who said to me, everybody's going to think you're an expert on everything. You're not. And I know very well I'm not. And so I try to limit my statements to things I have some experience with.
That's great, thank you. So because we are low on time, we're going to head back to Mélodie right now. But thank you all.
Thank you all for sharing with us your view about this theme. I wished we had more time to discuss with you because I thoroughly enjoyed getting to know what you think about all these themes and getting to know the humans really behind all these scientists. But unfortunately, we're already nearing the end of this session. However, before we do end the session, I'd like everyone to meet the two brains behind this event who made this event possible. So I'd like to introduce Christian Van Gysel and Gilles Gerbier, who are the two people who made this event possible. Gilles Gerbier is a professor of physics at Queen's University. And Christian is the co-founder of TEDxSaclay. Let me say a few words about this experience, and then we'll wrap up the discussion. So Gilles, your stage is yours.
Thank you, Mélodie. Actually, doing research is exploring new territories. This event, as was saying Mélodie, was the first ever. And this was actually exploring new territories. That was exciting, stimulating, but we did not know exactly where we were going. And even on the technical side, we have had problems that we are not expecting. However, this organization, the organization of this event, was an incredible drive. It was a lot of enthusiasm. And all the actors who participated made it possible and pleasant. So I would like to thank all my Canadian colleagues first who participated this adventure, in particular Art, Donna, Aaron, and also Rob, Sandra, Barbara, Patrick, Zach, Julie, and others. Last but most important, my most beautiful discovery was the great TEDxSaclay team, a factory of good humor, new ideas, professionalism, and in particular, Christian, besides me, co-founder of TEDxSaclay, with whom we started this very ambitious project that we led to the end. Christian, it has been a great pleasure to work together.
Thank you very much, everybody. I am like Patrick. I have no more my camera with me, so I have to share with Gilles. So thank you very much again, everybody. It was really a great pleasure to have all of you around this table and to share about physics, Nobels, and Terre, notre vaisseau. Thank you very much. Take care.